This video, we're going to talk about 4.4 spanning sets and linear independence. So we're going to be using the graphing calculator quite a bit for the matrix features. So I've got that over on the side. You can also use the Desmos matrix calculator if you would like. So let's start with number one, which gives us an S, a set of the vectors 2, -1, 3, and 5, 0, 4. And we want to see if that spans. We want to see if we can make the vectors that are given to us from this set as linear combinations. So question A is if the vector z equals -1, -2, 2 can be written as a linear combination of the vectors in S. There it goes. So A says z equals -1, -2, 2. So I want to start with 2, 5, and then -1, then -1, 0, -2, 3, 4, 2. And the book shows you all the steps to get that, with multiplying this one by C1 and that one by C2 and adding them together to get a matrix equation on the left that's equal to these constants on the right, and then turning the coefficient matrix into this. It's just take the x components and add them together here to get this x component and these y components here on this row to give you this y component, and these z components to give you the z component. And you see that it might work, but we run the risk of we've got only 2 rows and 3 rows and 2 columns here. So it might work. We'll see. But we see potential issues with that. So we've got a 3 by 3 matrix here. When we augment it, and we've got 2, 5, -1, -1, 0, -2, and 3, 4, 2. So 2, 5, -1, -1, 0, -2, 3, 4, 2. Right, we quit, come back to our matrix menu, go to math, look for our REF that's at the bottom, second matrix A, and we see that this RREFs to be 1, 0, 2, 0, 1, -1, 0, 0, 0. So this tells me that I can write Z as 2 times 2, -1, 3, minus 5, 0, 4. And that's Z equals that. That's equal to a -1, -2, 2. All right, let's go ahead and look at part B of that problem. Go ahead and just erase this part here since we have the same S and I don't want to rewrite all that. Part B asks us about vector V, which is 8, -1/4, and 27/4. So I'm going to go back into that same matrix and edit it, and I only need to edit the constant values that are on the right. Everything in the first two columns stays the same, so this changes to an 8. This changes to a -1/4, and this changes to 27/4. And that's my new matrix that I want to write down here. So this is 2, 5, 8, -1, 0, -1/4, 3, 4, 27/4. And to RREF that. RREF, remember, is reduced row echelon form. That's the same as Gauss-Jordan elimination. Just going to go back and get that same command because it's the same matrix. And I can change those fractions in my head here, so I don't need to do the answer to fraction command. So that's 1, 0, 1/4, 0, 1, 3/2, 0, 0, 0. So that tells me that V is equal to 1/4 of 2, -1, 3, plus 3/2 of 5, 0, 4, and that is equal to 8, -1/4, 27/4. Part C of this problem, asks if we can write W equals 1, -8, 12 from these vectors. Let's see if we can do that. Second matrix, edit, and we want this to be 1, this to be -8, that to be 12. 2, 5, 1, -1, 0, -8, 3, 4, 12. REF. Split second entry, and we get 1, 0, 8, 0, 1, -3, 0, 0, 0. What that means so far is that we have been able to use just the X and Y components and the to determine the coefficients here, and the Z component just worked out by our choice of our X and Y components. We'll see in a minute here if we get it to where the Z component comes out to be something different and we can't make it work. But so far these have worked. So we have 8 times, let's see, this is W equals 8 times 2, -1, 3, minus 3 times 5, 0, 4 is equal to 1, negative 8, 12. So let's go ahead and see if we can write D down here with U equal to 1, 1, negative 1. So we would want 2, 5, 1, 1, 0, 1, and 3, 4, negative 1. We want to RREF that. One, and negative 1. And there we go. That's our first one where we have a problem. So we get 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. So this tells me it's not possible, right? If I get a false equation like this, 0 equals 1, it is not possible to write U as a linear combination of the vectors in S. Okay, so keep going here to number 3. Very similar problem. 3 is given by S equals 2, 0, 7, 2, 4, 5, 2, negative 12, 13. That feels better because we have 3 components and 3 vectors. As long as none of them are linear combinations of the other 2, we'll be in great shape. If they are, then maybe we can't write some vectors in R3 with these 3 vectors. So let's start off with A. Part A says U equals negative 1, 5, negative 6. So we'll get a new matrix here. And this is going to be 3 by 4. You go ahead and write the matrix out before I put it in the calculator. So this is going to be 2, 4, sorry, 2, 2, 2, negative 1, 0, 4, negative 12, 5, and 7, 5, 13, negative 6. That. So 2, 2, 2, negative 1, 0, 4, negative 12, 5, 7, 5, 13, and negative 6. So that gives me 1, 0, 4, and that's negative 7 fourths. We have 0, 1, -3, 5/4, and then 0, 0, 0, 0. So at first blush, you're like, huh? How can I change that into a into anything useful to me? Well, basically what this is telling me is that I don't need to use the third one here. Well, I could get a parameter for it here to let that constant be t. Just let that t be 0, and I'm left with using -7/4 times the first one and 5/4 times the second one and 0 of the third one, and I'm good. So that's the easiest way to do it, is to let that t be 0 in your parametric equation and just use the first two. So let's go ahead and look at B, which asks us about V is equal to -3, 15, 18. Come back in here, change our matrix to match that. -3, 15, and 8, and that's 7. This to be 18. So we have vector 2, 2, 2, -3, 0, 4, -12, 15, 7, 5, 13, 18. We're going to RREF that. Second matrix F. That gives me 1, 0, 4, 0, 0, 1, -3, 0, 0, 0, 0, 1. And you see this false equation down here at the bottom that tells me V cannot be written as a linear combination of the vectors in S. Let's move along here to the next problem. Part C, using the same S. And it says W is equal to 1/3, 4/3, 1/2. Matrix, that's 2, 2, 2, 1/3, 0, 4, -12, 4/3, 7, 5, 13, 1/2. We'll want to RREF that. Second matrix, edit. Come on over to my constants over here. This is 1/3, and this is 4/3. And this is 1/2. And I'll change that to a fraction for you. Just remember that if you use the answer to fraction command, that you're not going to just have second entry. You have to go back 2 commands to get to your RREF. So math, answer to fraction. We're going to get that this is 104 -1/6, 0, 1, -3, 1/3, 0, 0, 0, 0. So that gives us -1/6. This is W equals -1/6 times 207 plus 1/3 times 245 plus 0 times 2 -12, 13. And let's look at part D, which is Z equals 220 -3. Two 20 -3. So I need to get past that answer to fraction to get my RREF. So this is 2, 2, 2, 2, 0, 4, -12, 20, 7, 5, 13, -3. Going to RREF that. We get 104 -4, 0, 1, -3, 5, 0, 0, 0, 0. So that tells me that W or Z can be written as -4 times 207 plus 5 times 245 plus 0 times 2 -12, 13. The other way you can set up this vector matrix, if you didn't figure it out already, instead of looking at the x components with the x component, and the y components with the y component, and the z components with the z component, take these vectors and write them downwards here and make your column matrices out of that, and then make a column matrix out of this one over here. And that's how you can form that matrix to test for linear independence, and we'll use that to figure out spanning here in a minute as well. So let's look at number 5. And number 5 asks us, let me see the directions for 5, because we've gone here to different kind of problem. It's also a linear combination problem, but with matrices, to ask us if matrix A is equal to 2, -3, 4, 1, and matrix B is equal to 0, 5, 1, 2. Let's see if these 2 by 2 matrices can be written as a linear combination of matrix A and matrix B. Basically, the same question does the set of, really what I'm asking is if I made S equals the set of 2, -3, 4, 1, and 0, 5, 1, 2, does that, can linear combinations of the matrices in set S, can they give us the given 2 by 2 matrix? So part number 5 is that we want A times 2, -3, 4, 1 plus B times 0, 5, 1, 2. You can call these C1 and C2 if you want to. Might as well. C1 and C2 equal to 6, -19, 10, 7. And so I'm going to get equations here that say 2C1 plus 0C2 equals 6. That tells me 2C1 equals 6, and C1 has to equal to 3. So then I'm looking at -3C1 plus 5C2 needs to be -19. I already know C1 is 3, so -9 plus 5C2 equals -19. -19. So 5C2 is equal to a -10, and C2 is equal to a -2. Let's see if that works out the rest of the way through here. If so, I have my constants. 4C1 plus C2 equals to 10. 4 times 3 is 12. Minus 2 is 10. That works. And C1 plus 2, C2 equals 7. 3, this is a negative, and a negative, and a negative here. So minus a -2, that's +4, equals 7, and that does work. So my C1 is 3, and my C2 is -2. So I have 3 times matrix A minus 2 times matrix B is equal to 6, -19, 10, 7. And there to number 9. It's not based off of these matrices anymore, so we'll just clear the canvas. That asks us about spanning sets. If the set of vectors given here, S, spans R2 or does not span R2. So S equals set of 2, 1, -1, 2. If these vectors are linearly independent, where the only way to get 0 from them is to have 0 of each of them, then I can go ahead and say that they will span R2. I can make any vector in R2 that I want to from any two vectors that are of that dimension. These are two-dimensional vectors. I can span R2 with them if they're linearly independent. So I'm going to test for linear independence here to see if the determinant of this is 0. Writing the column vectors 2, 1, negative 1, 2, and testing here 4 plus 1 is 5, which is not 0. They're linearly independent. And span R2. It doesn't look exactly like what we did just a minute ago, but it's equivalent to if I had set this up as 2, 1, negative 1, 2, and put zeros on the side to solve them. This would have a solution to it as long as the determinant of that coefficient matrix was not 0, which would be telling me that none of the rows were linear combinations of each other. If the determinant came out to be 0, there would not be a unique solution because I would end up with one of them was a linear combination of the others, and that's not good. That's not going to make a spanning set. So we want and this is what I was saying, this gets in differential equations, we'll do this with functions, this idea, and we'll use this determinant idea to figure out if it's 0 or non-zero, and that we'll get there. It's called a Wronskian. But you test to see if the Wronskian is 0 or non-zero, but it's based off of this idea right here about a spanning set and the determinant of the members of the vectors that make up the set being set equal to finding the determinant, seeing if it's equal to 0 or not. So let's look at number 11 with S equal to 5, 0, and 5, negative 4, like that. So we have 5, 0, 5, negative 4. It's a negative 20 minus 0 is a negative 20, which is not equal to 0. So they are linearly independent. And S spans R2. So look at number 13. S equals, and they only give me one vector here, negative 3, 5. It should be obvious that that's not enough for me to span R2. I should need 2 linearly independent 2 by 2 vectors. So the most that I can get out of this is the line that this determines in R2. So S does not span R2. It just gives us a line in R2 made by this vector here, 21. S equals, now we're going into 3 space instead of 2 space, so we're looking at R3. We have negative 2, 5, 0, 4, 6, 3. It looks underdetermined to me. I need to check to make sure. Oh, I know it is because I need a third column and it's going to give me a row of zeros. So they're not going to be linearly independent just as soon as I throw that column of zeros in there to make the determinant. I've got 4, 6, 3, and to make this square to find a determinant, I'm going to have to throw in a column of zeros, which forces this to be 0. So they are linearly dependent. And do not span R3. And if I have 2 of the 3 dimensions necessary for, but I'm in R3, I can get a plane out of this. That should make sense to you if you've taken Calculus 3, that that you stay flat in one dimension and the other 2 dimensions go on forever. So that's what's going on here. So 23. We have S is equal to the set of 1, -2, 0, 0, 0, 1, and -1, 2, 0. So we've got the determinant 1, -2, 0, column vector 0, 0, 1, column vector -1, 2, 0, column vector. Let me go ahead and do that in my calculator. Second matrix, edit 3 by 3, 1, 0, -1, -2, 0, 2, 0, 1, 0, and I need second matrix determinant of second matrix A, -0 determinant, which tells me that somehow, some way, these were not, oh, it's right there. So R2 here is -2 times R1. So R2 equals -2 times R1. I can just see that right there. So they're not linearly independent. They're linearly dependent. And S does not span R3, and it would make a plane again because I end up with 1 row of zeros down there. I've eliminated 1 dimension, so I end up with a 2-dimensional infinite space there, and that would be a plane. Let's go on to 27. S equals -2, 2, and 3, 5. So we're going to set this up as, let's see what 27 asks. It asks if, so we're testing for linear independence here of these 2 vectors, and it's really the same thing. So if -2, 3, 2, 5, 0, 0, if I RREF that, what will I get? It's really no different though than asking me if this has a 0 determinant, but we just have different ways that we tell you to do that in the book here. So second matrix, edit 2 by 2, and sorry, 2 by 3. So I need to get that row of zeros. So that's -2, 3, 0, 2, 5, 0. That column of zeros is there for my constants. I want second matrix math, RREF, second matrix A, and we get that they are linearly independent. The vectors in S are linearly independent. Just write IND for independent, DEP for dependent. Let's go on to number 31. And it asks me the same thing, with S being equal to 1, -4, 1, and 6, 3, 2. So let's go ahead and second matrix edit. This is going to be 3 by 3. Yeah. So we have 1, 6, 0, -4, 3, 0, and 1, 2, 0. We get that row of zeros there. But that's okay because we see that we have C1 here has to be 0 and C2 has to be 0, which tells me that the vectors in S are linearly independent. Let's look at number 33 with S equal to -2, 1, 3 and 2, 9, -3 and 2, 3, -3. Set that up so we have 3 by 4. We have -2, 2, 2, 0, 1, 9, 3, 0, 3, -3, -3, 0. RREF that. Let's answer the fraction. We had -2, 1, 3, 2, 9, -3, 2, 3, -3, 0, 0, 0. RREF is 1, 0, -3/5, 0, 0, 1, 2/5, 0, 0, 0, 0, 0, So this row of zeros down here tells me that they are linearly dependent because I have the that parameter that gets used to make up the other rows. So row 1 and 2 depend on row 3 is what that tells me. So it's just an example. It looks like this, 3/5 t for whatever that constant would have to be, -2/5 t for whatever that constant has to be, and t there. So as an example of something that would work, if I chose t to be 5, this would be -2 and this would be 3, and it would work, but they're linearly dependent. That constant 1 and constant 2 depended on constant 3. So let's go ahead and look at number 35. Thirty-five says S equals 3/4, 5/2, 3/2, comma 3, 4, and that's 7/2, and then -3/2, 6, and 2. All right, I want to test for linear independence. So 3/4, 5/2, 3/2, 3, 4, 7/2, -3/2, 6, 2, 0, 0, 0, REF. So second matrix, edit 3/4, 3/4, 3, -3/2, 0, 5/2, 4, 6, 0, 3/2, 7/2, 2, 0. We want to REF that, and we get that this is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, which means that C1, C2, and C3 all have to be 0 in order for me to get the 0 vector, meaning these are linearly independent. And that is it for this video. We'll come back next time to talk about 4.5, which are bases and dimension. So basis and dimension. So let's come back next time for that. See you for the next video.